Alright, I was going to do a couple examples of optimization problems. So they all kind of work out the same way. You're going to have two equations. One's sometimes called the secondary or auxiliary equation, and then you're going to have the main equation that you're going to try to minimize or maximize. So let's look at this one. We want to find two positive integers such that the sum of the first and twice the second is 108. And then the product is a maximum. So we want to maximize. So our integers can be x and y. The sum means plus. So we'll have x plus 2y, and then it's going to equal 108. The product is going to be maximized, so we'll just call it p. And the product of the two integers will be x times y. Okay. So we have two equations. One is kind of the auxiliary or the secondary equation. That's the x plus 2y equals 108. The function that we want to maximize is their product. So I'm going to want to take the derivative of that. However, I want it in one variable. So I'm going to go after the variable that looks easiest to solve for. Now it'd be the x. So we'll go ahead and solve for the x. So x is equal to 108 minus 2y. And we'll go ahead and plug that into the equation that I would like to maximize. And then I'll distribute 108y minus 2y squared. That's going to be what my product function is. Now I'm going to go ahead and take the derivative, and then I'm going to set it equal to 0. Okay, and it's 0 when y is 108 over 4 or 27. So at 27 I need to check the derivative here. So if I look at this here, we could pick something like, I don't know, 10, and we'd see that that would be increasing or positive. And then I could pick something to the left, 27, like 30, and that would give me a negative. So I have increasing to decreasing, so I'm going to have a maximum there at 27 for the y. Now they want us to find both integers, so I'm going to plug 27 back in, and I get the x is 54. Okay, so 27 and 54 would be my integers, who has the property that the sum of the first one, which is 54, plus twice the second one, which is 27, has a sum of 108, and then the product is maximized. Okay, let's find the perimeter, or the minimum perimeter, for a rectangle of area 32 feet squared. So we want to minimize our perimeter, or maybe our fencing or something like that. So perimeter is going to be 2 lengths plus 2 widths, so we can just use x and y. You can use L and W, doesn't matter. So that's one of our equations. The other one's going to involve area, and area is length times width. And we're given that the area is going to be 32. So we're going to replace the A with 32. And then, so what we want to minimize is the perimeter function. So that means our other equation, the secondary or auxiliary equation, is the 32 equals xy. So we're going to solve that for one of the variables. It doesn't matter which one. It'll work out the same way. So if we solve for the y, we'll get 32 over x is equal to y. So we're going to go ahead and substitute that in. So 2x plus 2 times 32 over x, because that's what the y is. And we'll clean that up a little bit. 2x plus 64 times x to the minus 1. And I want to write it that way. Just a second. I'm going to write it that way so it's a little bit more friendly to take the derivative. So when I do take the derivative, derivative of 2x is 2. The derivative of 64x to the minus 1, the negative 1 comes down, makes it negative 64x to the minus 2. So we're looking for a horizontal tangent, and that's where the derivative is equal to 0. And that's when 0 is equal to 2 minus 64x to the minus 2. So we're going to go ahead and solve that equation. That's going to give us the equation 64 over x squared equals equals to 2, so if we add 64 over 2 to both sides, we can multiply both sides by x squared, and then divide by 2, and then take the square root of both sides. Okay, so we get plus and minus 4 root 2, but since we're doing minimalization and we're talking about length, we're going to throw out the negative. Okay, and then we're going to test around that. So testing something less than 4 root 2 would be like 1. So 2 minus 64 over 1 squared is going to be negative 62, so that's quite negative, so that tells us that our function's decreasing. And then we can pick something like 10. 10's bigger than 4 root 2. So 2 minus 64 over 10 squared will be 1.36, and that's positive. So we went from decreasing to increasing, so we have a minimum at 4 root 2. Now what I would need to do is to find what the other value is going to be. So we can use our area function and plugging in our 4 root 2 to find the other length. And in fact, both of them are 4 root 2. So to minimize perimeter, we need a square. Alright, this time we're given a rectangular solid with a square base, and that has a surface area of 337.5 centimeters squared, and they want to find the dimensions that's going to maximize the volume. So we'll draw ourselves a rectangular solid with a square base. So the base is x by x, and then the height is y. So the surface area is going to be, we're going to have two bases, and the bases areas are x times x, or x squared. So we'll have 2x squared, plus each side is x by y, and so that area is going to be x times y, so we'll have 4xy. The surface area is 2x squared plus 4xy. And we know what that is, so we're going to go ahead and replace surface area with what it's equal to. The volume of this is going to be base times height, so the base is x times x, or x squared, times the height of y. So volume is equal to x squared times y. We want to maximize the volume, so that's what we're going to want to take the derivative of and set it equal to 0. However, it's in both x and y, so we're going to need to solve our surface area equation for either the x or the y, and the y looks a lot easier to do that. So to solve that equation right here for the y, we're going to subtract 2x squared from both sides, and then we're going to divide by 4x. And that's going to give us y, and then we can plug that into the volume formula, and we'll have to work it out a little bit. Volume is equal to x squared times y. Nice thing is going to happen, that x squared here is going to cancel the x there, so we'll just have one x left to distribute through. And that 1/4 is a constant, so I'm going to bring it out in front. Okay, now that thing's ready to take the derivative, the 1/4 is just going to hang out in front. So v prime, or your volume, its derivative is 1/4, 337.5 minus 6x squared. In the interest of lack of real estate, you can solve this on your own, set it equal to 0, and you're going to get x is plus and minus 7.5, but we only want the but since we're talking area, we only want the positive version. So 7.5 is our critical number, and we're going to test our derivative around that. Okay, so I'm going to choose something smaller than 7.5. I'll let you crunch those numbers on your own. V prime of 2 is going to be positive, so that means we're increasing to the left of 7.5, and then we'll try something like 10 to the right, and we get a negative, which means the volume's decreasing. So when we go from increasing to decreasing, we're going to have a maximum at 7.5. And to find the y value, we have this equation right here. is solve for y. Let me try again. This one right here is solve for y. So we can go ahead and plug in x is 7.5, and we get 7.5 for the y. So all the dimensions are the same, so we actually have that the maximum volume is going to occur with the constraint of a certain amount of surface area is going to be a cube. Alright, let's do another example. This time we want to send a cylindrical package, and it can have a max combined length and girth of 108 inches. Length is how long the cylinder is. The girth is going to be the perimeter of a cross section. So we'll go ahead and draw ourselves a cylinder. We'll call the side X and then the radius R. So the combined length X plus perimeter of a cross section, which would be the circumference of a circle, would be a cross section. So we'd have a cross section in here. So all those circles would be the same perimeter or circumference. So 108 would be X plus 2 pi R. Our volume of a cylinder is going to be pi r squared times the height, pi r squared times x. Okay, so we want to maximize our volume, but the volume's in an r and an x variable. So we're going to have to solve for either r or x. And it looks like x is a little bit easier to solve for. So x is going to be equal to 108 minus 2 pi r. We'll go ahead and substitute in the volume equation. And then we'll distribute. So 108 pi r squared minus 2 pi squared r squared. I'm sorry, not r squared, r cubed. And then when we're trying to maximize our minimum, we're looking for critical numbers. Critical numbers happen where the derivative is equal to 0 or the derivative is not defined. So we're going to take the derivative, and then we'll be interested in when the derivative is equal to 0. And you can work this out on your own. One of them is easy to see. If r is 0 and r is 0, then obviously that's going to be 0. And the other would be 36 over pi. Okay, if the radius is 0, then that's not going to be very exciting. It's going to be a shape that doesn't make sense. So we're going to throw that one out. So r is 36 over pi. That's our critical number. And then we're going to go ahead and test values in our derivative. So we can test like 1. And when we test 1, we get positive, so that means we're increasing. Test something like 100, we get decreasing. So if we go from increasing to decreasing, we have a maximum. And then we already have x is equal to 108 minus 2 pi r. We know what r is. It's 36 over pi. Okay, and there's our dimensions. That's going to maximize volume and meets the restrictions of the girth requirement. Alright, let's go ahead and minimize the distance between the function y equals square root of x minus 8 and the point 12 comma 0. Remember, the distance formula is the difference between your x coordinates squared plus the distance between your y coordinates squared, and then we take the square root of that. So we get that from the Pythagorean theorem. Alright, so the distance would be the x coordinate is 12, and then the x value from our function squared minus the y coordinate is 0, and then the y coordinate of the function is determined by a square root of x minus 8. And then take the square root. Then we're going to go ahead and simplify, so we need to FOIL 12 minus x quantity squared. And I made a boo-boo here. This should be a plus. Sorry about that. I think I fixed it here too. Plus, and then the square and the square root are going to cancel each other out here, and we'll just have x minus 8. And we'll combine like terms and make it a little bit more friendly to take the derivative, because with all these, take the derivative, you set it equal to 0 to find the critical number, then you test around your critical number, looking for either increasing to decreasing or increasing to decreasing for either a min or a max. When we take the derivative, we're going to have to use the chain rule. So the 1/2 comes down, the base stays the same, and you subtract 1 from your exponent, times the derivative of the inside, which would be 2x minus 23. Okay. This junk right here, all of this, that's in the denominator. I don't care what that is. What I care about is when the numerator is equal to 0. So when is 23x minus, when does 2x minus 23 equal 0? That's what I care about. So that would be when x is 23 over 2 or 11.5. That's my critical number, so we're going to go ahead and test around that. Okay, so we go from decreasing to increasing around 11.5, so that's going to tell us that we're going to have a minimum there. And then we can use our y function to tell us what. You can use a decimal number instead of what I'm coming up with square root of 4 over 2, but that's what the y coordinate is. So 11.5 and square root of 14.2, that's going to give me the point of minimum distance. If you actually want to find the minimum distance, you now have the 2 points, so you would have the 12, 0, and this 11.5 square root of 14 over 2, and you would use that to actually find what the minimum distance was. One other thing that I didn't mention is the critical numbers happen where the derivative is undefined or it's equal to 0. So I didn't mention, but x squared minus 23x plus 1 is 36 has a negative discriminant, which is the b squared minus 4ac in the quadratic formula. If the b squared minus 4ac is negative, that means you're going to have imaginary numbers. So you're not going to have any x-intercepts, so that's never going to equal 0. So we're totally fine with that.